I'll be speaking today about escape problems, and in particular, as our sort of canonical example, we take the ionization of hydrogen in parallel external electric and magnetic fields. And in principle, we'll be looking a lot at the time domain in which we see that ionization occurs via pulse trains of ejected electrons. And we'll connect this also to fractal structures and the chaotic dynamics. This is work at the College of William and Mary with myself and primary collaborators John DeLoss. A number of undergraduates have also helped, Steve Knutson in chemistry and Nahum Zobin in math. So we've tried to bridge the spectrum between multiple disciplines. Well, I'm a physicist, so I should begin with an experiment. These are some experiments that were performed several years ago at Nordham's group in foam. And here's a little cartoon sketch of what's going on. A short laser pulse impinges on a rubidium atom and is absorbed by the valence electron, which creates an outgoing wave, electron wave, which one can model semi-classically as an ensemble of classical trajectories moving away from the nucleus in all directions. Now, we apply an external electric field, which pulls the electrons down toward the detector. Now, some of the electron trajectories are ejected directly downhill towards the detector and create this initial prompt pulse of electrons. Other electron trajectories, however, are launched uphill, are turned around by the external field, and returned to the core, where they scatter, again, in all directions, creating a second pulse, and subsequent rescattering events create subsequent electron pulses. And so we have this train of pulses which strikes the detector. Here's some typical data that they see. You can clearly see the initial prompt pulse of electrons, followed by several subsequent pulses. And there are sort of three important points I'd like to make about this plot. The first is that the decay doesn't occur exponentially, as you might naively expect, but rather occurs in these sort of discrete packets. The second point is that they can actually measure these discrete packets with picosecond time resolution. And the third point is that the behavior of this pulse train encodes some of the classical information of the system. In particular, the peak-to-peak spacing here is roughly one return time of an electron trajectory to the core. Now, we won't be talking about the rubidium problem per se. It really serves as sort of motivation for us to consider, for us, a simpler problem, which is hydrogen in both electric and magnetic fields. Now, if we don't have the magnetic field and we just consider the electric field case, then a simple classical computation shows us that we just have a single pulse. Okay, this is because there's no core from which to scatter, so we don't get these subsequent pulses, as we saw in the rubidium case. But if we turn on a magnetic field, then we again see a pulse train. But despite the fact that this pulse train will look qualitatively similar to the rubidium case, the mechanism for the creation of this pulse train is entirely different. It's not core scattering. Again, there's no core to scatter off of. Rather, it's due entirely to the chaotic dynamics of the classical system. And so with that in mind, we'll relate these pulse trains to a particular fractal structure. And in this fractal structure, we'll see that there are both regular features, which we call epistrophes, and irregular features, which we call strophes. An epistrophe is actually a term from rhetoric that we introduced, and it means a repeated ending following variable beginnings. So to understand where the structure comes from, we'll need to delve into the classical dynamics of escape. And in particular, there's a homoclinic tangle which organizes the classical dynamics. The influence of this tangle can be seen on the fractal, and we'll prove two main results, or we have proved two main results. I won't be able to go into the proofs here. One is what we call the epistrophe theorem, and the other is the epistrophe start rule. And to prove the epistrophe start rule, we've introduced sort of a novel kind of symbolic dynamics that we call homotopic lobe dynamics, and I should have time to describe that in some detail. And I'll conclude by coming back to the electron pulse train and showing how this fractal structure influences the structure of the pulse train. Okay, I think for this audience, I can skip over that. Here's a classical computation. This is hydrogen in an external electric field only. And this is an analog to what we saw in the rubidium experiment. In other words, this is the ionization rate or the rate at which electrons strike the detector as a function after time, or as a function of time after the initial absorption of the laser pulse. And we see that we have more or less one pulse of electrons that comes out and decays exponentially. If we now turn on a magnetic field, we see a very different situation. Again, we have this large direct pulse of electrons, but it's now followed by this pulse train. Okay. I should make a comment about how these computations are made. Again, this is a purely classical computation in which we assume an initial ensemble of outgoing trajectories away from the nucleus, which begin at a precise time and have a precise energy. So, of course, this is not a very quantum mechanical computation. To first order, what we can do is essentially a quasi-classical computation in which we assume an initial minimum uncertainty Gaussian wave packet in phase space and then propagate that classically. If we do that, we'll average over initial energies and starting times to acquire this red curve here. Okay. And the point I want to make is that even though the sharp pulse structure is sort of washed out, you can still clearly see the influence of the pulse structure here and so forth. So we believe that one should be able to witness these pulses in actual experiments, as in the rubidium case. Okay. Now I'm going to have to cheat a bit with my technology to go over to some animations. Okay. The red circle up here represents our distribution of outgoing trajectories. Immediately,
Green.
I'm sorry, what did I say?
Red.
Well, maybe I'm colorblind. Yes, exactly. The green circle represents the outgoing electron trajectories. And as time evolves, they're pulled down by the electric field towards the detector. And here they come. And they'll strike the detector here in a moment. Here we go. This is the beginning of this pulse. And if we allow time to continue, we'll see that the pulse begins to peter out, and we're left up above with trajectories which are more or less all bound forever. We have an exponential decay. That's a very simple situation.
This is constant electric field, no magnetic field.
Constant electric field, no magnetic field. Magnetic field is what's going to happen next. Okay, again, we have the initial trajectories going out in green, are pulled downhill, and it looks more or less the same. The magnetic field restricts us to a smaller width. Here we strike the detector. Again, this is the direct pulse. But now as time evolves, we see something new happening. We see these two lobes here getting pulled down, and they're going to strike at exactly the same time right here, which creates our second pulse. And this can continue. We see another pulse pass by, and there are two more pulses striking. And we have a big pulse coming up right here. This pulse is actually somewhat special. You really can't tell from what I've told you thus far, but there's a certain pattern to these initial pulses, a nice regular pattern. This pulse, however, breaks that pattern. And so one of the things we want to study is what are the regular structures and what are the irregular structures that we in some sense can't predict, except numerically. And if this continues on, you see pretty much what happens. You have sort of an infinite number of pulses which rain down, and they start to overlap and become very complicated. We're not really going to be concerned too much with the long-time behavior. We want to study the initial pulse structure. Oops, you don't want to see my LaTeX code. There we go. Okay, so to study the ionization rate, these pulse trains, it's helpful to study the escape time plot. That is, the time it takes a trajectory to escape or strike the detector as a function of the initial angle at which it's launched from the nucleus. So if we're launched directly downhill, here we hit the detector very quickly. But as we raise this angle, it takes longer and longer time before we reach some critical angle. And above this critical angle, all trajectories are bound forever. So we have infinite time. We can translate this into the ionization rate down below by more or less just taking the slope of this curve. That's the 0B field case. Let's add a magnetic field now, and we see a much more complicated structure. Again, we have these direct pulses or direct trajectories down here, and we have the trajectories up here, which are bound for a long time, but the transition region now is much more complicated. You see that there are these nice smooth regions in here, which we call icicles. This is following Jaffe and actually others before him who observed such structures in initial angle final action plots, which Bill Miller has popularized over the years. This plot is also similar to some of the plots that Gregor Tanner showed yesterday, in which you have these infinite time singularities here. In fact, their occurrence will be due to the same sorts of chaotic structures. The point to notice here is that each of these icicles generates one pulse of electrons. So you can match up icicle to pulse, like this. We have this guy. Here we have a double pulse, and so forth. So the moral of the story is if we want to understand the structure of the electron pulse trains, we should try to understand the structure of the escape time plots. Okay. And of course, it has some sort of a fractal structure to it. And what I'd like to illustrate here are what the regular features of that fractal structure are. There are numerous sequences of icicles. Here I've illustrated one such sequence with these red dots. So we have one icicle, 2, 3, 4. In fact, it's an infinite sequence converging to this point here. And we call such a sequence an epistrophe. So that's what I mean by an epistrophe. It's these regular sequences. And we see these epistrophes throughout the escape time plot and on all scales. So here's another epistrophe, the blue epistrophe, which converges to the right edge of this icicle, and the green epistrophe, which converges to the left edge of this icicle. Okay. Let's skip that. But the epistrophes are not the whole story. There are additional segments. So the epistrophes give you some sort of self-similarity, recursive structure. But there are additional segments. I've denoted a couple of them here with the green asterisks, which do not fit into these regular sequences of epistrophes. Okay, they tend to break the self-similarity. And they are very important segments or icicles in their own right. Okay. And so what we have is something that we call epistrophic self-similarity. That is, you have the epistrophes, the regular self-similar structures, at all levels of resolution, but you also have these sort of variable, somewhat surprising segments or icicles which arise at all levels of resolution. And these strophe segments are not some sort of transient behavior that go away in the asymptotic limit. In fact, what we see is that they tend to dominate. Okay, so why am I using these terms epistrophe and strophe? Well, a strophe is a term from rhetoric or poetry, music, what have you, and a strophe is a stanza, or perhaps a stanza with some irregular structure. Epi is used in the sense of the end or the outer part of, as an epidermis or epilogue. And so an epistrophe is the ending of a strophe, or in particular, a regular repeated ending of a variable beginning. And it's really best illustrated with two examples. In Lincoln's Gettysburg Address, back when we, well, I'm not making any political comments right now. Lincoln's Gettysburg Address, he was a very good speaker. Lincoln said, "Government of the people, by the people, and for the people shall not perish. Of, by, and for, the irregular beginnings, and the people is the regular repeated ending, or the epistrophe." Also in the book of Genesis, you have the 6 days of creation. On each of those 6 days, you have various different activities which take place. Those are the irregular strophes. But at the end of each day, you have the regular repeated epistrophe, and the evening and the morning were the nth day, where n runs from 1 to 6. It's phrased a little more poetically than that, but... okay. I'm just going to briefly go through some introductory discussion of the dynamics. I just want to show how the homoclinic tangle evolves in the dynamics of the hydrogen system. So here I think we can all agree on this. This is the Hamiltonian in cylindrical coordinates for the hydrogen atom in parallel fields. We have the kinetic energy term, Coulomb potential term, the magnetic term, and the electric term all set equal to the energy. I've assumed that the angular momentum about the field axis is 0 for simplicity, so we have a nice 2 degree of freedom problem. Now, I can work in scaled variables, which eliminates explicit dependence on the electric field, and I use the standard trick in the Stark problem of introducing parabolic coordinates. And I regularize the Hamiltonian to remove the Coulomb singularity. And so the important point is that this results in an effective Hamiltonian, which is, again, kinetic plus potential. The potential is now a nice smooth potential energy, which consists of three terms: a term that depends only on the u parabolic coordinate, one that depends only on the v coordinate, and a coupling current term between the two, which you notice depends on the magnetic field squared. So what this tells us is that if we have no magnetic field, then indeed the u and v oscillations decouple, and we no longer have chaotic dynamics. Here is a plot of the potential energy. The nucleus is right here at the center, and so escape occurs by running away from this center and going out over a saddle point here and out one of these exit channels on either side. And let me just illustrate a couple of sample trajectories. Here's a direct trajectory. Of course, they can look much more complicated. They can go out on the left side as well. Actually, the escape phenomenon can be well defined because there is a periodic orbit that's bouncing right here near the unstable fixed point, near the saddle here in the potential. And this is a so-called periodic orbit dividing surface that I think Laurent Wiesenfeld will talk about probably in his talk. We'll use the standard trick of introducing a Poincare surface of section. We'll take our surface of section to be the v-axis here, with PV as our conjugate momentum. And so the periodic orbit dividing surface, which is this periodic orbit that's bouncing around in here, will be a fixed point of our Poincare surface of section plot. So let me show what this looks like. One thing I should mention is that we will always be considering above the barrier escape. So unlike Stephen Cray's talk yesterday, we're not interested in any sort of tunneling phenomena. Okay, here's the surface of section plot. Here's this periodic orbit, which is now a fixed point of the dynamics. Of course, this is the case b equals 0, so everything is nice and integrable. The red curve is the stable manifold. The blue curve is the unstable manifold. And we see the usual situation for integrability, where the unstable manifold of one fixed point exactly connects with the stable manifold of the other fixed point. Our line of initial conditions is shown here in green. It represents all trajectories that begin at the nucleus but going out in all directions. A trajectory that begins down here will march off in the generally southwestern direction, and that corresponds to these escape times here. The critical angle corresponds to the intersection point here because it lies on the stable manifold of this left fixed point, and so it will asymptote over here and never escape. If I'm in this region, of course, I also won't escape. And that corresponds to this region up here. Now let me add the magnetic field. And we see things become much more complicated. Of course, we now have a tangle. We still have the right and left fixed points, and they're stable and unstable manifolds, but they now do not coincide. Rather, they intersect transversely, forming this very complicated structure. Now, if I blow up this region, like so, we'll see that the stable manifold in red, I've shown intersecting the line of initial conditions 3 times. Each of those intersections will correspond to an infinite time orbit. In fact, I've only drawn part of the stable manifold. Of course, there are an infinite number of intersections, which gives rise to an infinite number of singularities here. So in some sense, on a very basic level, the reason why we have these icicles, and therefore the reason why we have the pulse structure, is because the unstable manifold intersects our line of initial conditions an infinite number of times. Okay, I'm going to shift from a heteroclinic tangle to a homoclinic tangle because it's much easier to talk about one fixed point than two. In fact, the heteroclinic tangle that I showed before can be mapped into a homoclinic tangle just by identifying points through the origin. Okay, there's been a lot of work on homoclinic tangles and phase space transport, and we're basically viewing the ionization problem as a problem of phase space transport. Just to mention a few names that have influenced us a great deal are Jaffe and Wiesenfeld and Easton and Wiggins and Ram Kadar and Christoph Jung. And there are many others, and we're building on their work. So here I have an unstable fixed point with its stable and unstable manifolds, which intersect transversely at this point P0. this defines a region of the phase plane that we call the complex. You should view the complex as corresponding to the neutral atom, or to the bound system. And escape out of the complex corresponds to ionization. Okay. Now, if we continue the stable and unstable manifolds, we see that we actually intersect numerous regions in the phase plane called lobes. In particular, I'd like to concentrate on this purple lobe, which we call the escape zone E-1. It's inside the complex. But under one iterative of the map, it maps to E0, which is outside of the complex. There's a similar capture process. This capture zone C0 is outside of the complex, and under one iterative, it maps to the capture zone C1, which is inside the complex. So escape and capture occur via this so-called turnstile. Now, once we're outside of the complex, that is, once we're in E0, then we will map to E1, E2, E3, and then go off to infinity, thereby ionizing. Now, if we want to understand how we escape from the complex, we should look at pre-iterates of E-1. So E-2, shown here, contains everything that escapes in 2 iterates. E-3, everything that escapes in 3, 4, etc. Now let me put a line of initial conditions on this plot, and we see that the line of initial conditions intersects E-1. This will give us a segment of the line of initial conditions that escapes in 1 iterate. That will correspond to 1 pulse of electrons, if you will. Similarly, E-5 also intersects the line of initial conditions, which will give us a pulse that escapes in 5 iterates. And if we continue these lobes backwards, of course, they become very complicated, intersecting the line of initial conditions many times, creating many late-time pulses. Okay. Now, we'll introduce 2 quantities to describe this tangle. One is a local quantity. It's just the Lyapunov factor, or the largest eigenvalue about this unstable fixed point. We call this quantity alpha. The other quantity describes the global topology of the tangle, and it can be understood in the following way. You can imagine a scattering trajectory coming in along these green lobes, then entering the complex, running around for some number of iterates before escaping out along these purple lobes. The minimum number of iterates such a trajectory can spend inside the complex is what we call the minimum delay time, d. And it's nice to just go through the example shown here to see what is the minimum delay time. We map from C0 into C1, that's 1 iterate, then to C2, C3. Now C3 intersects E-3, so some of these trajectories map to E-2, E-1, and then escape. So we have a total of 5 iterates inside the complex, and you can get no fewer. Now, just a general comment. Homoclinic tangles are a very general method of escape and phase-space transport in classical dynamics, and can be applied not only to ionization problems, as I'm doing here, but also to molecular reactions, ejections of a planet or an asteroid from the solar system, fluid convection, and so forth. So this is a very general phenomenon. In fact, we've looked a bit at the microwave cavities that Sridhar spoke about, and we believe you should be able to see these exact same epistrophy structures and pulse trains in escape from a microwave cavity. Okay. The discrete time dynamics gives rise to a discrete time escape time plot. That is, this black curve here is the number of iterates it takes to escape. I've superimposed on that the original icicle plot here, which is the continuous time escape time plot. And we notice that their structures, in particular the singularity structures, are really exactly the same. Each icicle is just rectified into a single escape segment. And since the discrete time dynamics is easier, that's what we're going to concentrate on. Yeah. Okay. So here is one of these discrete time escape time plots with iterate number across the top, plotted as a function of the line of initial conditions. And the point here is that you can see the epistrophe structures very easily. So here is one of these prominent epistrophes, this shown with this red arrow at 5, 6, 7, 8 iterates, etc., converging to a line up here. We see this epistrophe converges to the lower end point of this escape segment, and this epistrophe converges to the upper end point of this escape segment. And this is a general fact, that you will always see an epistrophe converging on each endpoint of every escape segment. So this is this sort of recursive structure that we see. But I also illustrated several of these strophe segments, which are these surprising segments that don't fit into the epistrophe structure. Okay. And again, notice that this segment tends to be one of the larger segments. especially at this iterate number. So these strophe segments will create large pulses and will be important for actual experiments. Okay. The decay of the epistrophes is exponential, and that's what I'm showing here. This is a plot of the width of escape segments within 5 different prominent epistrophes from the previous overhead. And we see that we get this very nice exponential behavior. The decay rate is given just by that Lyapunov factor of the unstable fixed point. So you can relate the structure of the homoclinic tangle to the structure of these escape time plots. Okay. And the decay is, in principle, only asymptotically exponential, but the convergence is typically very rapid. Okay, and all of this has been summarized in a precise result that we've proved, which we call the epistrophe theorem. And this is just sort of a sketch of what the theorem says. It says that, again, on each endpoint of each escape segment, you have an epistrophe which converges to it. This convergence is geometric in the asymptotic limit with rate alpha. And in fact, you can say something stronger, which is if you take any 2 epistrophes, just by an overall rescaling, you can lay one exactly on top of the other, at least in their asymptotic tail. Okay. I can give a very simple, intuitive proof of the epistrophe theorem. Let's consider this escape segment here, and imagine we want to prove that there's an epistrophe that converges upon it. Well, let's just take this point and iterate it forward so that we're in the neighborhood of this unstable fixed point, blow that up, and do a linear analysis. So here's this unstable fixed point. I have my stable manifold and my unstable manifold, my line of initial conditions in green. These purple guys are escape zones. And if you just consider the linear map, then as you map these escape zones backwards, their widths are compressed by alpha and their heights are extended by alpha. And so eventually, this sequence must intersect this line of initial conditions in an epistrophe. That's what these intersections are. These are escape segments. The rate at which this epistrophe converges to this point is just the same as the rate at which these guys are compressed. That is, it's just alpha. Now, this is just an asymptotic behavior. It tells us nothing about when this segment occurs, when the first segment of the epistrophe occurs, and it tells us nothing about these initial measures. But as I said before, the convergence does tend to be rapid. Okay, and I'm just repeating what I said there. It also doesn't tell us anything about any additional segments we may have. It tells us we have these epistrophes, but there may be additional stuff, and that's what we call these strophes. Okay. You can see the importance of the strophes by looking at some long-time decay data. I'm not typically concentrating on the long-time decay, but in this plot I will. This is a discrete time ionization rate. That is, it's the total amount of flux coming out, not as a function of time, but as a function of iterate number. And what we see here is this nice exponential decay at the very beginning. This corresponds to one prominent epistrophe. It's followed by another epistrophe, and they start overlapping, and you start to lose the resolution of each individual epistrophe. But what we see emerging is some sort of emergent exponential decay here. This decay rate is not the same as that of an epistrophe, which is much more rapid. Okay. Now, if I cut off the data here, you might think we'd hit some sort of asymptotic limit in which we would just continue to see nice exponential decay. But in fact, that's not what has happened. You see some late time bursting. This is about an order of magnitude greater than what you would expect to see. And if we go out to even further times, here's this emergent exponential decay. Here's this sort of late time burst. We see that maybe it's repeated here, and then we get some gobbledygook here. At some point, you sort of stop to trust our numerics. But clearly, well, we've looked at this. It's not clear whether it's exponential or algebraic, and we've asked these sorts of questions coming to no particular conclusion. But the important point about this slide is that all of this behavior, including this emergent exponential decay, is in fact not due to the epistrophes, but is due to these additional strophe segments. So it just illustrates the fact that if we want to understand really what's happening at long times, we better understand these additional strophe segments. Okay, so let me now return to the epistrophes and try to characterize them a little bit better. What can be said about how the epistrophes begin? This is a practically important question because the initial segments of the epistrophe tend to be the larger segments, and so we'd like to know when they occur. And what we can just observe from this graph is the following, that this epistrophe begins 6 iterates after this segment here. And the same is true of this guy. This epistrophe begins 6 iterates after this guy. Same is true here. In fact, if you look throughout this plot, you'll see that epistrophes always begin 6 iterates later. Okay, and we call this the epistrophe start rule. Now, similar kinds of rules have been seen, for example, by Easton and Ram Kadar and Jaffe and so forth in a variety of different situations, but they've typically concentrated on the structure of the homoclinic points of the tangle. And here what we're looking at is an arbitrary line of initial conditions in which we also see these similar patterns. Now, these patterns are a consequence of the global structure of the tangle. And I just want to give you a flavor in this sequence of slides of what I mean. So here's a relatively simple tangle. We have this lobe, C1, intersecting this lobe, E-1. We have our green line of initial conditions, as usual. And let's map this situation backwards. So the lobe C1 maps back to C0. The X that's in this intersection would then be over here. The lobe E-1, well, its base maps over to here, and its tip must go around the X, so its tip must go over here. Now, it's well known that the stable manifold can't intersect itself, so the lobe E-2 must look something like this. Okay, this is sort of a standard picture. Now, what's important here is that based solely on the topology, we see that we must have an intersection between the lobe E-2 and this green line of initial conditions. That is, we have a segment that escapes on 2 iterates. That must be there. We could have more intersections if there were some additional kinking to this lobe, but we have at least one. Now let's map it backwards again. The X maps from here over to here. The base of E-2 maps closer to the X point here. We must connect this point to this point without intersecting any of the previous lobes, and so we get something that looks like this. Now we've been forced to have 2 intersections. That is, we have 2 segments that escape on 2 iterates. Again, we could have more. And these segments lie on either side of this first segment here. If we do it again, we find that we have at least 4 segments, 8 segments, and et cetera. You can sort of go on arbitrarily long as your finger doesn't cramp up as you're drawing these squiggly curves on the plane, which I've done for many hours, and is quite amusing to do. You can fill up your time on the train or the plane or whatever your favorite form of transportation is, though I don't recommend doing it in the car, especially if you're the driver. But what you'd really like to have is something that's more algorithmic, something perhaps you could have your computer do instead. And so with that in mind, I'd like to take about 10 minutes or so to describe a new approach that we have to the study of tangles. In part, I'm telling you this because it's directly related to the structure of these pulse trains, but I'm also telling it to you because I think it's a nice, cute idea and gives us maybe some more insight into the study of tangles. Essentially, what we're doing is developing a new kind of symbolic dynamics. So in the standard kind of symbolic dynamics, you've got Markov partitions and so forth, and a symbol sequence represents a trajectory. Okay. Here, a symbol sequence represents a path in the plane. Okay. We will express this symbolic dynamics using the language of homotopy theory. Okay, we don't really need any deep results of homotopy theory, but it forms a nice algebra for us to use. So in homotopy theory, what do? Well, we connect points in the plane, avoiding certain holes with paths. Okay. So what I first need to do is specify what points are allowable endpoints for my paths. And often one chooses just a single point in the plane, but here I'm going to choose an infinite number. I'm going to choose the homoclinic points Pn and Qn. Shown here, this is P0, this is Q0, and we use all of their forward iterates and all of their backward iterates. So we have an infinite number of possible endpoints of curves. Now, homotopy theory in the plane is rather boring if you don't have any holes. So I'm going to judiciously choose my holes to be intersections of, let's say, this escape zone, E-1, and this capture zone, C1. And I call this the hole H-1. So the curves can't enter the holes. Okay. And not only will we use H-1, but we'll use its forward iterates, which converge here, and its backward iterates, which converge over here. So we have homotopy of paths connecting an infinite number of points in the plane and avoiding an infinite number of holes. Okay. Now, in homotopy theory, what's really important is not so much the individual paths. Like, for example, this path which connects this point goes around this hole over to this point. We're not so interested in that path. We allow arbitrary distortions of this path so long as we keep the endpoints fixed and we don't distort through one of the holes. So I'll often be talking about paths, but what I really have in mind are equivalence classes of paths, homotopy classes. Okay. We can define the product of two homotopy classes simply by concatenating curves. So, for example, if we want to multiply this curve here by this curve here, we end up with a resultant curve that begins at P0, ends at P1, and does something like this, allowing distortions. Okay. This product defines a groupoid structure. Now, I use the term groupoid rather than group, like you might be used to in homotopy theory, because I have multiple base points. And I can only multiply two curves if the endpoint of the first curve is the beginning point of the second curve. And so we have a restricted product, which formally gives us a groupoid. Okay. Now, an interesting part of this whole analysis is that the tangle itself gives us a wealth of paths to choose from. In particular, there are four principal classes of paths. We have the escape zone here. This is an escape zone E sub n. It has a path which is defined by its unstable boundary and a path that's defined by its stable boundary. That's these two paths over here. The script represents the path, and the non-script lowercase represents the homotopy class. We also have the unstable boundary of a capture zone, Cn, and its stable boundary as well. That gives us two more classes of paths. Now, the dynamics on the plane gives us a dynamics on the paths. This path here, U0, maps forward to this path, U1. So we see over here that the dynamics acting on these paths just gives us a shift in the index. Okay. So in that sense, the dynamics is very simple. But this is really not the best way to view the dynamics. It doesn't really contain any information. So we're going to take a page from linear algebra. In linear algebra, if you want to express a linear operator, what do? Well, you can choose a basis. You can apply your linear operator to each element of that basis. And then you can re-express the result in terms of the original basis. We're going to do the same thing here in Spirit. We're going to choose a basis of the groupoid, by which I mean a minimal spanning set of the groupoid. And to do that, what do we need to do? Well, we need to be able to connect any point here to any other point. For example, this point way up here. Okay, so that's certainly one requirement. And how do we do that? Well, we just traverse the boundary of the tangle here. We go around like this, and we can get over to this point. So we must include in our basis all of these boundary segments. That is, all of the S segments and all of the U segments. And so we include all of these guys here. We also need to be able to circumnavigate any hole in order to have a basis. So this hole up here, for example, we can circumnavigate by traversing this E0 segment. In this hole, we can traverse the E1 segment, and so forth. So all of these upper holes we can traverse by the En segments for n between 0 and infinity. And all of the lower holes we can traverse with C segments from 0 to minus infinity. So that's what we have here. That leaves us with only one more hole that we need to go around. And that's this hole in the interior. In general, there will be D holes, where D is this topological parameter that I introduced earlier. And we can traverse this hole in a natural way, either with the C1 curve or the E-1 curve. By convention, we'll choose the C1 curve. So that's why we've added the 1 here. Now, what do? We apply the map to each element of this groupoid and express the result in terms of to each element of the basis, and we express the result in terms of the basis, just like you would do in linear algebra. If you apply it to a U or an S element of the basis, it just shifts this n index, which keeps us in this range. Obviously, it's the entire range. So we don't need to do anything special for the dynamics on these guys. The same is true here, because obviously, if I shift n 1 greater, we'll stay within this range. But down here now, if I apply the map to C1, I'll get C2, which is not in my groupoid. So I have to, not in my basis. So I'll have to expand C2 in terms of the groupoid basis. And this is the formula. Let me sketch it out in the figure so you can see how this is done. This is the curve C1. The curve C2 will begin here, go down around this hole, and come back. And the assertion is that that curve is the same as traversing E1 backwards. The minus sign just refers to the backward traversed curve. So we traverse E1 backwards, then C1 backwards, then U0 backwards, then E0 forwards, C1 forwards, E1 forwards, and this little segment is S2, I guess, yeah. So the assertion is that this curve here goes around like this, and back is the same as this curve, which you can pretty much just do in your head, distort one into the other. So the point is that all of the interesting dynamics of the tangles contained in this equation. So this is our method of symbolically mapping forward the basis elements of the groupoid. Okay, how does this give us an algorithm to compute escape segments? That's what we really want, is we want some way of determining this minimal set of escape segments. Well, we consider a line of initial conditions, which, for the sake of argument, we'll just say joins one homoclinic point to another homoclinic point. It could, for example, be this line. It also has to avoid the holes. And we'll express that groupoid element in terms of the basis. Now, here I'm just going to choose L not equal to C1 for simplicity. So my line of initial conditions is somewhat artificial physically, but it's this curve that goes around like so. And now what do is I take that line of initial conditions and I map it forward symbolically using this principal equation here. So the map applied to L naught, which is C1, just gives us this expression here. Now, I've underlined this U0 segment because it's particularly important. The U0 segment is a segment which passes through this escape zone E0. This is a segment that has just escaped. Remember, E0 is outside of the complex. So each occurrence of a U0 segment tells me when something has escaped. Here I only have one such segment. But now I'm going to map L1 forwards again. And this U0 will map forward to this U1 guy here. But now notice that we have a C1 sitting here. The C1 is sort of a seed for future escape segments, because C1, via this equation, produces another U0. So this C1 maps forward into this sort of awful expression, but the important point is you have this U0 here, and there's a C1 on the opposite side, which gives you a U0 here. And so what we see is that on the second iterate, we have two new segments that have just escaped, and they lie on either side of the original segment. You can do it again to get L3, and I'm not going to go through this in detail, except to point out that you now have 1, 2, 3, 4 new segments that have escaped on the third iterate. So this is a very clear-cut algorithmic approach you can use to compute this minimal set. Okay. So in short, what do we have? We find that global topological considerations give us a minimal set of escape segments. And it's actually not hard from this algorithm that I sketched out to prove that after a sufficient number of iterates, this minimal set displays this epistrophe start rule. That is, you can explicitly prove that you will spawn new epistrophes delta iterates later, one on each side of a given escape segment. And we have a formula for delta. It's just one greater than that minimum delay time of the tangle. So again, we're relating the topological structure of the tangle to the properties of the escape time plot. Okay, and then the segments that don't appear in this minimal set, these additional segments due to additional twisting of the lobes, are these strophe segments. Okay, so in practice, or in principle, we should be able to get some understanding of these strophe segments by putting more topological information into our symbolic dynamics. And that's sort of current interest. Running a little short on time, but let me just make a comment that here is a surface of section plot for this saddle center map that I'd shown before. Now I've included some data interior. We see this large stable zone, and in particular we see this period 5 island chain surrounding it. Well, between these stable islands, we're going to have unstable fixed points, and these unstable fixed points will have their own stable and unstable manifolds, which go out into the chaotic sea, intersect with these primary stable and unstable manifolds, twist them all around, and in some sense that is responsible for creating additional intersections, that is, additional escape segments, and hence additional pulses. That's sort of what I'm sketching out there. And this period 5 behavior is actually visible in the data. So these blue arrows point to these unpredicted strophe segments, and we see that there's a very clear period 5 behavior to them. Okay. So certainly these unstable, or certainly these island chains are responsible for at least some of the additional structure that we see. And that's perhaps not surprising. Okay, let me summarize my results with this following graph. Let me illustrate what each of these panels are. You've seen basically each of them before already. This is the pulse train here. Down below, I show this icicle plot, which is this escape time plot, continuous escape time plot. And I match up each pulse with its corresponding icicle. So, reflected over here is the discrete time escape time plot, which allows you to see the epistrophe structure more clearly. And I've illustrated up above the relevant epistrophe structure. So here we have the direct segment. That corresponds to this segment down here, which corresponds to this icicle over here. And if I continued it further down, you would see that it matches up with this direct pulse right here. The A epistrophe, A1, A2, A3, A4, converges on this direct segment. That corresponds to these segments down here, which, if you flip over, corresponds to A1, A2, A3, and you can't really see A4. We then connect each of these icicles up to their corresponding pulses. So here's an A1 pulse, A2 pulse, and an A3 pulse. So the point is that these epistrophes of escape segments give rise to epistrophes of pulses. And in fact, the decay of the pulses, of the total flux in each pulse, is also given by this same rate alpha. So the pulses decay with the same rate as the epistrophes do, as you might expect, at least in the asymptotic limit. But again, that limit's obtained very quickly. The time between pulses is roughly equal to 1 period of this periodic orbit that defines escape. And one can also witness the epistrophe start rule. Here we create 2 new epistrophes on either side of this segment 2 iterates later. In this case, delta is equal to 2. And then we have a B epistrophe and a C epistrophe that converge on the upper and lower endpoints of the A1 segment. Again, that corresponds to these sequences here, which correspond to these icicles here. And the B1 and the C1 icicles give rise to these 2 pulses here. Now, these guys happen roughly 2 periods beyond this segment here, because these segments occur roughly 2 iterates beyond this segment here. Okay. So the epistrophe start rule is also evidence in this pulse structure. We see the next 2 segments in the B and the C epistrophes right here. They're exponentially suppressed, and so they're not very easy to see. So the epistrophe structure completely characterizes the initial structure of the pulse train. But then what we find is that the next pulse, this very large prominent pulse, corresponds to this segment here, which the star indicates that it's one of these strophe segments, corresponds to this guy over here and this guy over here. Clearly, this guy is not part of one of these epistrophe sequences. And so it's clear that the strophe segments correspond to pulses which should be experimentally important. Okay, let me summarize. So based on, I haven't said much about quantum mechanics or even semi-classical mechanics. I've justified the classical computations with a quasi-classical computation. And we don't expect interference effects to be important for the early pulse structure, because you really don't have 2 trajectories coming together and interfering. But for longer time behavior, once pulses start adding on top of one another, you're going to start to see interferences. Okay. So right at this point, we've only done classical computations. And what we see is that we decay with this nice pulse train. And we've been able to relate this pulse train to the chaotic dynamics of the classical system, which, of course, is a consequence of the magnetic field. And we've been able to identify specific properties of the pulse train which reflect the regular, that is the epistrophe structure, and the irregular structure, the strophe structure, in the chaotic dynamics. And so we've been able to make predictions on the number of pulses, the pulse heights, the spacings between pulses, and so forth. And just to think about, what's on the horizon for us, we'd like to understand the strophes at the same level as we understand the epistrophes. I have one of the nice things about this homotopic lobe dynamics approach is that it seems to be relatively straightforward to include additional topological information. And that's something that I'm currently working on, to be able to predict when strophe segments will occur. And we have good reason to believe that this is certainly related to the periodic orbits, and we like to make that connection more explicit. Another interesting thing is, as you do these computations, of course, you see pulses coalescing and bifurcating. It would be very interesting to study this behavior in detail. Sometimes in the process of bifurcating, the pulse amplitude will increase significantly, and so that might be some way of being able to observe large pulses at long times, perhaps. I made some very vague heuristic comments about long-time decay. We haven't really thought about it in detail, but it would be interesting to see, once you start to put in strophe data, whether you can maybe say something about the long-time behavior. Already made comments about the importance of interference. Another experiment that you could imagine doing, instead of doing a short-time pulse-type experiment, would be a continuous wave experiment where you would expect to see interference patterns, perhaps, on your detector. There have been some experiments recently that have been able to see such interference patterns for the case of an electric field only, and it would be interesting to see what it would look like if you added a magnetic field. In some sense, you would be imaging a chaotic atomic wave function. And we would also really like, someone to do experiments to verify all that we've been talking about. And that's it. Thank you very much.
Mm-hmm. Firstly, in the very nice epistrophes history, did you see some pruning happening? That means some branch that disappeared for some non-genetic reasons.
Some
pruning. That means that
right.
For some reasons, these orbits do not exist.
Okay, as I understand pruning, it usually corresponds to the existence of periodic orbits. And in our case, all of this was... It's a scattering problem, so we haven't concentrated on the periodic orbits except that principal periodic orbit, that principal fixed point. And so I gave some indication that we might start looking for influence of additional periodic orbits, but that's not something that we've currently done. If you're talking about the epistrophes themselves, no, we don't see any epistrophes that are missing. They're always there, and that's something that we've proved. Mm-hmm.
Strophes. One of the avenues we look for is looking at active trajectory to see what's going on. For example, it could be that these trajectories are, if I remember well, your Poincare section there.
Mm-hmm.
Maybe you show.
Let's see if I can remember where it is. This is PDF, so I don't have these. Here? Okay.
You have long, big islands there.
Right.
It might be, it happens, that some trajectory get trapped for some time into the island, stay an infinite amount of time there, and then go out.
Yeah.
You lose all the hyperbolic speed lost.
Right. Yeah, so that is an effect. Okay, you remember the plot I showed of the long time behavior, where you had this emergent exponential decay and then this long time burst. Okay, that was actually for this map, which is not quite the hydrogen system. This is a model map here. And we interpret that, actually, I think for that data, we had used a line of initial conditions over here instead. We interpreted that data as something running around, getting pulled into some sort of an inner tangle defined by the stable and unstable manifolds of these unstable periodic points. Getting pulled in here, running around for some number of time, and then getting kicked back out. Now, some people might interpret it in terms of a Cantorus as well. And so we believe that we do see that kind of behavior.
This groupoid, it seems that this groupoid analysis of this tangle is new. I've never heard of anybody talking about these before.
I haven't either.
Is this a way of characterizing, in some sense, is it a way of putting homoclinic tangles into equivalence classes of topological structure?
In some sense, yes, and that
simple classification.
Okay, that's a good question, and this is something that has been addressed for a long time in terms of symbolic dynamics. What you're wanting to do is you're wanting to extract the relevant topological features of the tangle. What we have done is extracted essentially the large-scale kind of coarse or gross feature of the tangle. It's not a classification of tangles. You can't classify it just with that one parameter. As far as I know, there's no complete classification of homoclinic tangles, the topologically complete classification of homoclinic tangles. Because you'll have additional intersections. You'll have additional homoclinic points that are not included in this simple analysis. And in some sense, those additional homoclinic points are what give rise to these strophe segments. So these strophe segments occur because there's additional topological information that you haven't included. Now, one of the things that we believe we can do is, using this homotopic lobe dynamics, you can include additional topological information. So what basically this new approach has is you define a groupoid. The dynamics on the plane gives you a dynamics on this groupoid. Okay. And that dynamics is given symbolically. But by using more complicated groupoids and having certain well-defined rules for the dynamics on that groupoid, you should be able to characterize topologically more complicated tangles. So that's one of the things I'm actively working on.
Maybe I could comment a little bit, but whenever you have a structure like this, you have infinitely many small portions embedded in it, meaning subsets of finite type. The thing which you've done is you have, as you say yourself, you have extracted the most important coarse subset for finite type, having to do with this equilibrium point on the right.
Right.
And that's very good. Now, what usually happens is you have a competition between the Coulomb thing in the middle, which likes integrability, and this hyperbolic point. And the story which you're describing very well now is the stuff that's close to the to equilibrium point, and it's very important for transport, so it's a good thing to do. But of course, the full symbolic dynamics is much worse because it's competition between these two things, and it's full of islands, periodic orbits, etc. So that's one comment. So, I think you just have a beginning of it, but there's much more to it. And whether it's groupoid or not, that's kind of a matter of taste. I mean, maybe it's a smart way to do it. I don't know, other people.
Whether it's, I'm sorry?
Groupoid or not, it's a matter of personal taste,
right.
Because you can do symbolic dynamics in many ways. Now, the other thing is, you will always have algebraic. There's no way you will not have algebraic power decay because, just the picture tells you that you have intermittency in this because any ergodic trajectory can come arbitrarily close to the torus, which you see, or any other subtorus. So, so there'll be fast exponential stuff and a power law.
In the line.
And you're probably, by doing your stuff, you're probably capturing correctly the fast exponential things because, stuff that gets transported out has to go through this trough, and so you're controlling the gate. You're the keeper of the gate. And you speak Greek, and it's all wonderful. But, it's going to be, you're in the same soup as the rest of us. It's very, very horrible.
Yeah, I know. If I could just make one comment, I think where this sort of homotopy idea is important for our particular problem. It's because we have this line of initial conditions, and so you can just see that the homotopy type of this line, if it goes down here or if it goes way over here or something like that, will give you different sets of escaping segments. And so this is our way of including information about the line of initial conditions into the problem.
I mean, it's extremely important for short time pulses that you're studying. It's
right.
Extremely important. For asymptotic behavior, it's irrelevant.
Yeah, because you have all this ergodic mixing and so forth. And certainly, if we are going to press to longer times, we would want to go over some sort of statistical approach and look at correlations and so forth. So it's not something we've concentrated on yet.
It may sound like a somewhat peculiar question, but looking at tangles like these with your groupoids and so on, and the way that you have, imagine that you were trying to do the same thing in a discrete geometry.
You mean instead of discrete time, or maybe in addition to discrete time, discrete space?
Of course, you're not going to have infinitely many things there. And so, and yet a lot of the same technique and the same insights can be applied in such a reasons why you would expect it to not give. How would you see your expectation of the difference in what you would have in these cases?
Well, it's a question I haven't thought about in detail because we're dealing with continuous systems. I think it would depend in some sense on what class of discrete maps you considered. If you had a very high density of points and your discrete map was defined so that it imitated something which is smooth, then we would certainly expect to see the same kind of behavior. I mean, that's essentially what we're doing on the computer. If it starts to become a very coarse discretization, then you have to talk about what kinds of maps, and are you close to continuous in some sense, and then all bets are off. I wouldn't want to touch it.
Okay, any other questions or comments? So let's thank the speaker again.
Thank you.